Let's take a look at some control fundamentals, control strategies. This particular presentation is going to focus on general, just fundamentals of controls, control strategies, and specifically we'll be kind of dealing with systems that would maybe be more advanced as a general rule, generic enough for a typical building automation system, which can vary from a small residential system to even the bigger system. So these are universal to all of them as we go through this. So there is a handout that you will have, which is the 145 M311 PowerPoint Chapter 9 Control Fundamentals. Let's get started. This particular module, we're going to focus on the basic elements of a closed loop control system and exactly how that is. There's actually such a thing as open and closed loop system. We'll take a look at that. The different control outputs, algorithms that they would use in the systems, which are typical of most all of those systems that we'll be dealing with. So first one we'll hit up on is the control system. It's generally the system, the brain of the system, your controller is going to make decisions based upon information, based upon feedback, a number of those things. So we'll take a look at that. So I'd like to start out right away and let's take a look at closed loop, a closed loop system, a closed loop, what we call a closed loop control system, and specifically we're going to start to look at these. Now this is slightly manipulated from what you have in your textbook. In your textbook there was a figure that had was figure 9.1 or 9-1, and what I did was I put numbers on each of those blocks to represent some of what their function is doing or what they are trying to do. So I would say a majority of our control systems are actually going to be a closed loop feedback. And this would be, of course, everything from a residential system that would be your simple room thermostat all the way to a more advanced system that might be controlling a commercial building or a boiler system or an air conditioning system. It could be any of these. So when we first start out with block 1, what I want to do is on block number 1, specifically in block 1, that's representing this block 1 right here. That is representing some input sensor, such as, like, say, it could be outside air temperature. It could be actually no, not outside air temp. It could be room temperature. It could be boiler water. It could be something that can be manipulated. It could be chilled water. It's something that you're going to sense as a general rule, and you're going to do something with that. So in this particular case, for this loop, for a closed loop, it definitely will not be outside air temperature. It would have to be something where we are going to be able to manipulate that based on something that we can control. So that would be how we would identify that. Number 2, and obviously back to number 1, specifically on an open loop system, that is where it likely would be something related to, like, outside air temp as an example. So anyway, so let's take a look at the second one. So on number 2, okay, that's my controller. So my controller is actually going to house most likely the settings. So what do you want to have for your settings? What do you want for a set point? What do you want for temperatures or it could be anything. It could be humidity. It could be temperature. It could be chilled water, hot water, room temperature, any number of variables. And this has to actually have a set of instructions. So this is actually going to contain something called an algorithm. Okay? And we're going to we'll talk more about the algorithm. They're also going to have settings or set points as an example. Let's just say that this has to be somehow programmed to some extent. So it has to be somehow manipulated. So the most common example that we deal with in our industry certainly is going to be some sort of an electronic controller So that's typical. Now, the controller, number 2, is going to actually provide us an output based on this input from 1 and based on the set of instructions that it has. It's going to provide you an output, which will then, of course, go to your number 3 would be your control device. So the control device could be a boiler, it could be a zone valve, it could be a pump, it could be the signals could be are very numerous. So the output signal, as an example, could just simply be a simple on-off type signal, or it could be a 0 to 10 volt, or a 2 to 10, or a 4 to 20 milliamp signal. So that is based on the programming or the matching of what type of output can your controller provide you, and then of course you have to then of course select the control device to actually match the signal that it can provide as an input. It wouldn't do you any good to use a variable or a manipulated, a modulating type controller if the controller can't provide you that output. So you have to match those things. So these two have to definitely be, let's say, they have to be matched together to meet whatever their outputs and inputs can be. But that's typical. It's going to provide me an output. Now, what I'm expecting to do at that point then is that output of that controller has to provide me some sort of a change in the manipulated variable. So, in other words, the water temp has to see a change. We have to change that. The air conditioning, the humidity level, whatever it is that you are trying to control, you're expecting that to be manipulated to provide more heat, to provide less heat, something like that. Then, of course, the output of the expected manipulation of that variable should be providing some sort of a manipulation of the heating load, is what we want to see. So, and this is where block number 4 represents. So it's just simply, block 4 is just simply saying this is what the heating load is. So this might be, I need to maintain this building at 70 degrees, 75 degrees, whatever it might be. It has to represent something like that. Then, of course, the last of the blocks, block 5, is going to be something that senses that variable that you are controlling. So, did we see a change in the room temp? Did we see some manipulation of that, whether it's a boiler hot water temp, or it could be chilled water temp if it's a water chiller? And of course, that system has to provide, the key element here is this loop here, is it has to provide you a feedback. And the feedback has to go back to the controller to say, hey, this is what you just did. This is how you manipulated this. This is what, when you change the control device, this is where you saw the change in that. So there's a number of examples that we could provide or give to that. So like I said, it could be chill water, hot water, it could be indoor air temp, it could be a number of those things. But that simply represents the closed loop system. So you could pretty much define a closed loop system as something that's going to provide you some sort of feedback into the controller at some point that says this is what we did based on your decisions or how you were working on that. So that's essentially a closed loop control system. All right, well, let's take a look at the next one. A closed loop control system is, you're going to have things that we'll talk about in this one here, and we're going to specifically hit up on some control theory. And in my control theory terminology, I'm going to talk about all those basic things that we are typical control systems have to understand. People that are working with a control system have to have some concept of. We're going to look at the processing algorithms. We'll take a look at the 3 main types, which are essentially proportional, PI, or proportional integral processing, and also the proportional integral derivative processing, which we call PID. So there's P, PI, and PID. And then, of course, we'll look at the last one is we'll look at the controller output types that are in our system. So let's take a look at the first one. The first one in our control theory terminology is going to be the simple set point. Now, the set point, we always figure the set point is what are you trying to maintain? I want my controlled variable to be maintained at X temp. I want my relative humidity maintained at this percentage. I want static pressure to be maintained maybe at 2 inches, or as an example. These are all examples of what you want. So this is really pretty much figured as what is it that you're wanting you really want to maintain is what you'd like to have. So that's really what you want to be looking at. So this is very significant in understanding the set point of what you really are looking for. And sometimes it's not easy to know exactly what that temperature or pressure or what it might be. So let's take a look at the next one. And the next one in control theory is what we call control point. Now in here there's a number of things that we'll be dealing with. So the control point is what I would call the actual temp, the actual temperature that would be sensed. So the control point temperature may not actually be the set point. In fact, oftentimes it's not. So the control point might be, it could be a little higher, it could be a little bit lower. It really depends on how the system is actually functioning or providing that control of that. So it is I would say in a majority of systems, rarely are you actually maintaining set point, depending on the level of sophistication of that system. So some of the limitations are going to be that will determine how far away from that you might be would be really the algorithm. That's one factor. The differential, and it may even be the throttling range might be another control parameter that would be, another term is called proportional control of that throttling range. So we'll do that. So how do we, to simplify that, in my picture down here, I have a control point. It's really, what am I getting? That's really, where is it controlling? So you'll notice the blue line is representing what we call the control point. So sometimes they're above, sometimes they're below. A lot of this is dictated based on how you have that program or that controller, let's call it calibrated, based upon that set point. So that's kind of the one way we would look at that. The offset. So what do we mean by offset? So offset is the deviation away from the set point. It's how much variation is occurring between the set point and where am I controlling it. So you'll notice the offset changes based upon the building load and based on how much heating, cooling that you might be providing. In this spot right in the middle, I'm going to change it to my pen here, and this spot right there, you'll notice that our offset is 0 because our set point and our control point are equal to each other. But in this spot right here, our set point is 74, okay, and the set point is 74, and in this case my offset is actually 2 degrees away from that. So our whole let's say that our whole distance away, the entire distance away from, in this particular case here, would be having a throttling range. I'm going to put this down here. The throttling range or proportional band is actually the difference between the higher and the lower. So that's actually going to be a throttling range of 4 degrees is how that would be. So there's actually, because of the way they calibrated it, our let's say our throttling range is 4 degrees, And being that the set point was in the middle of the two points based on our throttling range, plus or minus 2 degrees, that's where we have a throttling range of 4, and our offset is a variable function in this case. So the overall total swing is only going to be 4 degrees in this example. All right. So let's take a look at the next one, control action. So in control action, sometimes in some controllers, we have to identify, will this controller be reverse acting or direct acting? We have to tell it how it's going to work. And that is, in some cases we can do that, in some cases we can't. It depends on the controller. So a controller that is more of a universal controller, there's a really good chance that you're going to have to say, you're going to have to answer this question or program it to say, all right, I want this to open up on a rise, or I want it to close on a rise. So you have to identify whether you want it to be direct acting or reverse acting as the signal. And there's other ways that they'll deem that. But all of our controllers will do this. Everything from a pneumatic controller all the way up to a high-end DDC control system are going to have this. So what does this mean? So in direct acting, what it simply means is, in direct acting, what it means is the controller's output would increase as the sensor's input would increase. So I want to show you this example down in the bottom left here. In this example, we happen to have a DDC system or some sort of an electronic controller. It has a sensor that provides an input. So a sensor provides an input. Now, with a rise in the temp here, I would have to then tell this output of this controller, what do you want the output to be? Do you want it to go up? Do you want it to have an increased output based on an increased sensed input? And if that is indeed the case, that would be, of course, a direct acting loop. So then the output would be higher. And this very well could mean that the voltage might be higher. In this case, the milliamps would rise up. So we're using an electronic controller that might be a 4 to 20, a 0 to 20 milliamp type of a controller. So in my example here, if I see that, we sensed that it was 65 degrees in the room. And at 65, it's going to, based on the settings, we're going to have an output that represents 0 output or 0 milliamp signal into the transducer in this case. That would then, of course, provide you the lowest amount of demand out of this controller to provide control of this valve. So that's what it would end up doing. Now, as the room temperature is starting to rise, so for example, when the room starts getting warmer and warmer and warmer, and maybe we're up to 70, then the milliamp signal is increasing out of that controller, which then this is going up and it's rising, and we see a larger input into the transducer, which of course then provides you some output action. So maybe that would provide us an increase in pressure in this case. So milliamps go up, pressure goes up, and we provide that control. That is very typical of most systems that we would have to do. So in other words, your sensor reads your input temp, your controller responds to that. It provides an output pressure that would be higher in this particular case. As it gets warmer and warmer and warmer, it provides more output, and it changes the normally open valve and starts to close it down. Is typically how that would end up working. So that's kind of the general idea. That is what we mean by direct action. The opposite of that, quite simply, would be reverse action. And reverse action is, let's call it the exact opposite. With an increase in temperature, we would see a decrease in the output signal. So the output is going in the opposite direction as the input in this example, and that's called a reverse acting loop. Now, as this output controller, the output of this is changing, we're going into this particular device, which of course is providing, with a decrease in milliamps, it's providing us actually a decrease in that pressure. Now, one thing I want to point out here is we have a situation where the controller has a reverse acting loop, and it's actually controlling a device that is a direct acting device, is the way that it's set up. So it's a direct acting device. Now, this direct acting device basically is a system that you provide, and whatever you provide for the input, if you provide more input, it provides more output. So there are times that we have to look at what it is that we're controlling. Hey, what do I need to do? In order for me to get more output, do I need to provide a lower or a higher input on this? So the graph is what I would be looking for with a device like this, so I would know whether, when I look at my control system, I can kind of determine that, whether, hey, what do I need to do? Do I need to make it reverse or direct acting as the output on there? So in this graph, what we can see is that at 65 degrees, we are going to have an output that's maybe 18, 19 milliamps as an example. And at 70, as the building is getting warmer and warmer and warmer, you can see the output is actually decreasing. So we're down to maybe 12 and a half milliamps as an example, and that's just simply closing. Now in this example, we're showing a normally closed valve, and that this is one of those where we have to look at saying, okay, how is this going to work? So in order for me to give, if you're trying to heat a building with a normally closed valve, then you recognize that as the building starts to get warmer and warmer and warmer, I would need to, as you can see on the bottom here, as the building gets warmer and warmer and warmer, what's my control loop going to do? Very rarely would you ever see this used for a heating system in a lot of cases. It's more common that you would see this used even sometimes in chilled water systems, but this is one way to do it. It could be a computer room heating system, whatever might be used in there as an example. But this is one of these where in this example, we're showing a hot water system. We're using a normally closed valve. So when it gets warm in there, I don't want a bunch of output on there, and that's essentially what it's doing. So you have an output. As this rises, this goes down. This decreases the signal, and then of course it tells this valve, hey, I want you to close or go back to your normal position. So that's essentially a reverse acting. So the sensed variable and the output are in opposite directions. So the next one that we're going to talk about is what we call control theory, or in fail safe. And there's a mode that we oftentimes use. It's called fail safe mode. And what we have to do is we have to determine, based on the application, how do you want your component to fail. So the action of that controller has to kind of match or be appropriate for whatever that application is. So if you're controlling static pressure, how would you want this to fail? Now, if you were controlling static pressure on a fan system, you certainly would not want to have it where the fan would default into max capacity. So you potentially could blow up your ductwork. If you're dealing with a heating system, you maybe very well likely would like to have that heating valve open as a fail safe in a lot of cases. And it's kind of you just have to figure out how that system or that application should fail. A lot of times in the control specifications on your commercial jobs, they'll actually specify how they want fail-safe. What do they want as the fail-safe mode? So you'll do that. So in this example, we're showing, normally open heating valves will always use direct acting controllers. as a general rule. In reverse acting controllers, if we were going to place in a reverse acting controller, if we're going to place a normally open heating valve, the heating valve would open as the temperature rises. That would be the exact opposite you want. So it really rarely ever is ever going to be done that way. So I just put a note in here about the controller never really properly controls a normally open heating valve with a reverse acting system. It just wouldn't do that. And in this particular parameter has to be programmed or selected in some of the controllers, as I had talked about. So that's related to the control action. And again, it depends on how advanced that system is. So how do we typically figure this out? As I had mentioned, normally what I do is I start out with the application and I say, what am I controlling? I want to do temp control. I want to do heating. I want to do cooling. What is it that you're wanting to do? It could be humidity control. And then the next thing is, how do I want that control device to fail? Do you want it to fail open or do you want it to fail closed? So that's a little bit on fail safe. It's something that should always be considered in your application. The next one that we'll look at is something called system throttling range. And also we'll look at system proportional band. So let's take a look at this. So the system throttling range, STR, I'm abbreviating that as, it's a change in the variable, whatever it is I'm measuring, could be temp, that causes the control device to travel from one end of its stroke all the way to the other. So as an example, we could say the controller's output signal would vary from, the controller's output will vary from 0 to 10 volts DC over a change of X amount of degrees. So let's say 70 to 78 as an example. So this would mean that with the valve wide open and the valve fully closed, I will have a system throttling range that will be between 70 and 78, or a system throttling range of 8 degrees. It doesn't always mean that it's going to be 8 degrees. Certainly doesn't mean that it has to be 8 degrees away from set point. It just simply means that is the range or the throttling range of the control system or the system in this particular case. So in the example here, that would require a valve that would change its position over a 10 volt DC span, is what it would kind of mean if I were using a 0 to 10 volt signal. So that maybe this becomes 0 volts on a open valve, 10 volts on this. So I'm going to give you one example here that is something that I've had to deal with in the field. And in a situation where maybe I happen to have a 5 volt DC span valve. So let's say I have a valve that operates between 5 to 10 volts DC. Okay? On some valves you can actually select the starting point. So in that particular case, if the actuator has a span that would be a span of 5 volts DC, even though your controller has an 8 degree throttling range that's set, your system throttling range would then of course be only half of that. So that in that particular case, this valve would go fully open at 74, and at 78 it would be closed completely. So that would actually be half of the controller's throttling range. So I say this simply because in some situations, in many situations, you're going to have controllers that are going to be able, especially variable controllers, you're going to have outputs that will be different than the actual device you're controlling. So it may seem very unusual and odd for you to program a system with an 8 degree throttle range in this example, because you'd say, well, I would never want my system to be varied by 8 degrees. But remember, what you're controlling, you're going to see 100% of your change in capacity over only 4 degrees. So in this example, so it's just something to be aware of. Now, what do we have to look at additionally? So one of the concerns that every technician has is that in the event that my system throttling range is a little bit too tight, or my throttling range becomes a little too tight, one of the problems I can have is that device will cause the control device to hunt. Now, hunting simply means it's going to it'll drive it open, it'll drive it closed. It'll do it just almost non-stop or excessively moving the device. And this is sometimes caused by having valves and actuators that are way over, maybe they're too big for the load. And that's difficult, and it happens. It happens an awful lot unless that system was able to manipulate the load based upon what the device is that you happen to be dealing with. Again, very challenging, and it's a very common problem to have a system that would maybe hunt. And again, damage to your actuators, the control will be swinging all over the place, so you'll have changes where you just can't seem to find a happy stopping point or a medium. So those are the things that you have to kind of look at. So again, just be a little bit careful in that. But that's throttling range. System proportional band is the same. It's the same thing as system throttling range. It's just another way to deal with it. All right. In Figure 9-2 out of your textbook, there was a picture there that showed a type of control that's called proportional control. Now, this is a simple control, and I'm going to show you a couple of examples of this. But the first one that we deal with is where we look at the output signal of that system is going to be the output signal will be dependent upon the error away from set point. So what I would call your deviation from set point. So in this example, I want you to, if we look at this picture, what we are doing is this little float that we're showing right there, that float, the higher the water is, the more that it closes that valve and it lets less water come in. And essentially the lower that ball is, let's say if it's this way, it'll open the valve up completely and let as much as it possibly can. So it has a full range of output. So the output of this, what you're getting as an output out of the valve, is so dependent upon where it is I would say representative of what you want as your target level of what the target level would be an example would be my set point as an example. That would be what you want as a set point. And then of course, the one way to do this would be if in this example, let's say that my drain valve gets opened up because, hey, I have a little bit more water demand or a little more load. What will happen then is that would, of course, drive this valve down. It would open up this valve, and it would allow you to feed more water. So it is really the output is so dependent upon deviation from set point. So that is a very common type of a system or a control system. That was the basis of all modulating and what I'm going to call analog type controls. So it has to have some sort of a proportional band or a throttling range of some sort. So in a little bit more on this proportional band, proportional controller. So the output signals I had mentioned is dependent upon the amount of error. So the amount of error away from set point, the deviation from set point, dictates the output. So in this example, it's a very common type of a control system, is that there are times where we will be maintaining, depending on the load and depending on the size of the valve or depending on the capacity of the system, there's times where we will maintain a temperature way up here. And in fact, with a proportional system, the only time where, in this example, where the set point and the control point are the same, where these two match up exactly the same, is the only time that happens is when the output, when your valve is at mid-stroke in this example, equals the building load or equals the load of the system. So that's really the challenge. So in other words, I've had numerous systems in the field that work this way, and I had customers that had a set point in a classroom, let's say, that were maybe 74 degrees, if we use this as the example. And what would happen then is we would typically calibrate the set point of this, whatever that thermostat was, we would calibrate it so that we would put the control valve at the mid-stroke position. So if that valve was let's say that valve operated between 0 to 10 volts, then we would likely set the output at set point to be 5 volts DC. And then, of course, if we wanted to set that valve up, so, well, I want that valve closed at, let's say 2 degrees away from set point, and I might have a 4 degree, in this example, let's say a 6 degree, or actually a 74 to 76 as a 2 degree throttling range in this example. This is actually a typo here. I didn't catch that. This is supposed to be 70. Whoops. Let me change that. This here should have been 72 degrees Fahrenheit, and this one is 76, so that's acceptable. That should have been 4 degrees. I didn't catch that. And so in my system, we would set up a throttling range of this controller, so 4 degree Fahrenheit throttling range. We would calibrate it so that our output would put the valve in its mid-stroke. Now that's perfect if you have a linear relationship. In other words, if at 50% you actually get 50% of the output. That actually rarely happens. There are very few valves that are that linear, and when you're talking about control valve operation. So it's no different than even an economizer actuator. If you give an economizer 50% and make it 50% open, you don't get 50% of the air. It just is going to be significantly higher than that. And it's a matter of how linear the application is based on its selection. But this is a common issue, and it's something you have to be aware of. So what does it look like? So in the example that they had in your textbook, I'm going to expand on that one a little bit. They show a processing algorithm, which this is the algorithm. This algorithm is going to look at the set point. It's going to look at the amount of deviation from set point based upon the throttling range, just like this picture is showing to the left side. It's going to then always be kind of dictated based upon the load. So the only time that you really ever are going to be at set point is only when the output of your control device and the building load are equal to each other. That's the only way that's ever going to happen. So what happens sometimes in commercial applications is you end up having to calibrate a system for this happy medium, where you might have the system is going to be set up to, hey, when we're doing cooling, we're always going to be maybe a degree or two warmer, and when we're heating, we might be a degree or two colder than the set point. And sometimes that just happens depending on the type of control strategy or system that they're using on there. So there is no way to correct anything other than purely the only way that I can make it so that I can make this tighter, that I can eliminate offset. The only way to do that is I have to make the throttling range lower. I have to make that tighter. But then you run into the problem. You run it, the lower you make that, then it becomes a question of, are you going to get hunting? And that's the other issue you have to concern yourself with. So it's a challenge. Let's take a look at proportional integral control. So PI, what we call PI control. So in integral control, what we're doing is we're taking the proportional control, which represents the amount of error, and then what we do is we also take into another account a corrective measure. And it looks at, well, how long have I been away from set point? So what we look at with this integral control integral control is we try to take that condition of controlling to something other than the set point a little bit less, what we call less objectionable than a proportional system. So when we look at, well, how long have you been away from that air, what it does is it attempts to make a manipulation of the output of the device, is what we do. So every time that it kind of reevaluates the algorithm and it looks at the feedback loop and it says, what are we getting? What is this temperature? So in other words, oh, look at here, we're exactly, 2 degrees, 2.5 degrees away from set point. Well, let's make let's go ahead and make a correction to that output so that we don't need to have it be somewhat proportional. So for example, and I'm going to show this in as an extra factor here. So let's say that I have a valve that is going to be open, 100% open at that point, and let's just say we put that as we're going to use a device that's going to give me let's say 10 volts DC. I'll use this as an example. And in this device, and in the lower part here, we're going to say this valve is going to be closed, and it's going to be 0 volts DC. All right, now, when you set up your throttle range, in this case, at 8 degrees, from here to here, your total throttling range, when that was set up as having 8 degrees, 8-degree throttling range, the device can make a corrective measure, and it says, well, with proportional, we would have, when we were 4 degrees away from set point, we would have changed the output to 0 volts, and we would have waited and waited and waited until something got warmer, and it would have done that. And then when we would deal with when we got closer and closer, then it started to change the output. Now what it does is it says, well, hold on, we've been away from this set point for X amount of time. Why don't we, instead of waiting for the temperature to change in this space, why don't we figure out what to do with the output? So then it'll automatically say, well, tell you what, we really want to be at 5 volts. So maybe what happens is at this point, we might figure out that we should provide an output of 5 volts DC right here and 5 volts DC right there. And when it does that, what will happen then is it'll try to make that correction. Now it'll look at that and say, why don't we see if we can figure out where to find that happy medium. So it's always recalculating what the output should be to do that. So this is one of these controllers or control algorithms that every single time that load changes, that controller is trying to make a change. It's trying to make the set point and the control point exactly the same, which would be logical. Why wouldn't you want to do that? Now, hunting could become a problem. So what happens sometimes is we will have excessively large throttle ranges that we'll put into the controller, way more than you would ever really think. So in other words, I've had controllers in the field where I've used, for doing zone control or room temp control, I put a throttling range of 8 to 10 degrees. And of course, I would never ever use a throttling range of 8 to 10 degrees if I had a straight proportional control. That would just give you way too much swing. So we don't typically do that. But with integral control, I can use that to change or to recalculate the output signal to minimize the hunting, is what I can do on there. So it will let the integral factor to try to correct that signal. And it's one of those things that you have to learn the controller and learn how that program or that is calculated. In some cases, you'll just use a little bit of experience. You might ask guys that you worked with or that are working for the company you're working with, hey, have you programmed these before? What kind of an integral function is going to work? Or you might get this from the control manufacturer that could assist you in that calculation on there. I've dealt with some systems that actually learned that. It was called a self-tuning loop, and I'll talk more about that in the next one. So a majority of the systems in HVAC don't respond like so incredibly fast. They actually can get away purely with a proportional integral control. This is really the ultimate control that's really all that we really need in a majority of our applications. So this is, I would say, without a doubt, PI control is definitely the most needed, simply because it gives us the ability to close up the gap. So eventually, this point right here, that point where the set point and the control variable are the same, this could be anywhere from 0 to 10 volts DC, depending on whatever the corrective measure is applied to it. So you don't have to wait as with a proportional signal. That's really, you're going to be completely dictated based on deviation from the set point. So that is proportional integral control. Many manufacturers will put this in their control. So, proportional integral derivative controller. This is called PID control. Sometimes you'll hear this called a PID loop, and that's all that is. It's a proportional, integral, and derivative control. What this control algorithm does is it processes it adds this ability to monitor the change of the rate of change, and then make those corrections to that PI logic loop. So if you recall, I'm gonna go back to this here. In the previous one, we said the PI loop, the output signal was based upon the amount of error that was the deviation from the set point, that was proportional, and how long did the error exist. So those two, proportional integral, and then of course the derivative is, well, how fast is it changing? So when it sees that rate of change, it's trying to throw another loop in here, another calculation that says, well, let's make those corrections like lickety split. Let's make them really fast, so we can make this correction with a derivative function on here. So derivatives are rates of changes, and there's a calculation specific on how to do that. Now, fortunately, a majority of our systems that we use in the field really don't respond, or they don't change that fast. They're, a good example that I can recall ever, needing to do anything like a derivative loop would be maybe if I were doing some static pressure control on a duct system, where, let's say, if I have a damper that closes super fast and I need this frequency drive that might be controlling a fan speed controller to, hey, I need you to slow down really, really quick. That might be an application where derivative function would be needed, but rarely do we see anything. Certainly never room temp control would you ever need a derivative control. But I will tell you that a majority of the manufacturers will actually they will put derivative or PID simply because it doesn't really cost them anything to put in their controllers, and they'll say our control does PID, and it's more of a marketing thing than anything. It's really not necessarily needed. But one thing that I do need to point out is, if you do have a PID loop, generally the derivative function is going to be usually a very small parameter. So I want you to be super careful if you ever have to deal with these, because you can get a lot of hunting if you don't have this set up correctly. So you have to, because they're looking at rates of change, and so much of this is so dependent upon what it is that you're controlling, how much of a change in output do I get. So if I change this valve by 10%, how much of a change in the actual controlled variable am I getting? And that can be very challenging. So just be careful with that. I had mentioned about these self-tuning loops. So in the higher level systems, there's such a thing called a self-tuning loop or a learning mode. And I dealt with some of these where what it would do is you'd put the system into a learning mode. And the learning mode would drive the actuator or the valve fully open and fully closed. And then it would actually measure how much of a change and how fast did it change all at the same time. So it knows the output, it knows what it was doing, what the valve is doing, and it's trying to learn how to automatically calculate the derivative and the integral function. So in a self-tuning loop, that will work for many of the systems. However, a good example is where I felt that it probably would almost need to relearn at different times of the year would be, for example, an economizer loop. In an economizer loop where you're driving a control valve, an actuator, fully open or fully closed, because the outside air temperature will change so much that it's not as simple as, well, my variable is, you're going to see a different change in the variable based on when it's colder outside versus when it's maybe a little warmer outside. So it doesn't always work perfect, but it is still a function. The whole goal of this is to try to reduce the amount of error, again, based on the rate of change. So a good example of this, as I mentioned, just like in PI control, it's just another level bigger or more advanced than the PI controller in the fact that the output to the control device could be anywhere from 0% to 100% to try to reduce and try to make the control point and the set point the same. And as with PI control, you can have very large throttle ranges that are actually programmed in there. Don't be too worried about that. If it settles the control down, and then you allow your integral function and your derivative function to actually make those necessary corrections on there. So that's essentially what it is. So bottom line is, I think what I would identify or point out is the fact that my derivative control, or my whether it's PI or whether it's PID, ultimately these are all just trying to get it so that we control our room temps better. A derivative will just do it faster. And we, again, have to be careful with the hunting part of this. So this next little slide here is really just a summary slide of proportional PI and PID control. And I want to point this out to some extent. And you'll notice how at this point already, we have already figured out at this point right here on the derivative control that, all right, we are now satisfied. We are at, but as the load changes, it will then have to make adjustments, and it'll be able to pick this up really quick. So it responds really, really fast to its very fast response, a lot less overshooting, undershooting, if it's programmed correctly. If it's not, you're going to hunt all over the place. In PI control, you'll notice that it took a little bit longer for it to figure it out, and it wasn't until, after X amount of time that it figured, okay, now we're good to go. And again, it has to look at all of these factors of how this control is going to do it. So what all they're trying to do is they're trying to manipulate or eliminate any type of offset that might be over a certain amount of time that it's going to do. So the integral error over time will respond to the small amounts of error. It has the ability to automatically change the output signal to try to minimize offset. And then, of course, the proportional control is your control signal is completely proportional to the amount of error. It's essentially how much error based on the load. So in other words, if you have, as a general rule, if it's colder, in this example, what they're showing here, then I'm going to have an offset that's going to be lower than the set point. And if it's warmer, I'm going to have an offset that's going to be higher than the set point. The only time that you ever really set completely at set point is when the load and the control variable provide you the exact amount of output that meets what is really needed on there based on your calibration. So that was a little bit on proportional control, and proportional proportional, integral, and derivative control. All right, so the next one that we're going to take a look at is going to be some control loop system fundamentals. We'll look at output type of output devices, such as on-off control. We're going to look at what we call PWM, or pulse width modulation control, and we'll look at floating control, and then also modulating output. So let's get into that. So certainly on-off control, most technicians have heard of this before. It's essentially you have an output that is either going to be open or it's going to be closed. You have whether it's a set of contacts or a triac, any type of an output that is going to do this. So a system you'll notice the image or the figure to the right, figure 9.4. What we're looking at is we have a differential on this application here. So we have on-off temperature control operates with differential that's either going to be entirely below the set point or you could be centered on the set point. So this is something that we don't always know for sure how that control is doing its differential. Is it a plus differential? Is it a minus differential? So in other words, or is it smack dab in the middle? So this would be in this example in item B, in that example, you'll notice that, let's say that this represented a 10-degree differential, we might have it be, it would be basically a plus or minus 5 degrees swing. And then your set point would be right in the middle, and it would be plus or minus. Now, in this one here, your set point might be in the blue line, and then of course your differential maybe would be, in this case, maybe we would be minus 10 degrees. And if it's 10 degrees colder than that, as an example, then that would then trigger the action. So it really determines what you're looking at is you're looking at how much variation occurs between when it turns on and when it turns off. Most of the time, that's a parameter that is adjustable on electronic controls. Very rarely would it not be, but there are certainly some where you don't have any control over that, where that is. I've even seen some of the controls that have automatic calculation of the differential. So it'll learn the system. It'll actually figure out or recalculate what the differential should be based upon a cycle rate. So in other words, if you have a boiler that's short cycling, it will automatically manipulate this differential, and that's pretty neat. That's pretty neat to see that. So certainly one of the things that I have to concern myself with is with any type of a system, is it overshooting, is it undershooting, what is it doing? And the note that I made here is I said, well, the operating differential refer to the actual variation of the controlled variable as the system operates. So the operating differential in this case is going to be the actual temp measured here and what the full swing is. So all the way down in this bottom. So you'll notice that my operating differential is actually larger due to than really what you have for a differential. So you might have a control differential that is maybe plus or minus 5 degrees as an example. But because of the lag or the thermal lag or the inability to maybe control the output temp, or the hot water maybe going out from a boiler system is warmer than what it needs to be based on the load, you very, very well will see your operating differential be actually larger than what is needed, simply because of what I would call the time lag or the thermal lag of what you're controlling. So, and this could be the thermal lag of the boiler. This could be the thermal lag of your heat emitter, the mass of that, the building. Those things would be that. And the best example that I could give you that would which is one of the things where you will definitely see this, is if you happen to have a high mass, let's say a concrete floor that you're doing in-floor heating with, and if you happen to have, if you're putting 130 degree water into that in-floor heating floor, and the in-floor heating or the load is not that high in that room, as an example, what will happen is you're putting all this heat into the floor. Now it's waiting for that concrete to warm up. And so by the time the concrete kind of warms up and it dissipates some of that energy out of the concrete into the room, you have put so many BTUs into that concrete that the concrete's now going to overshoot. And even though that your control differential was set to maybe 2 degrees, but you may have an operating differential that could end up being 6-8 degrees because you're going to overshoot that space temp so far. This is something that you have to be aware of a little bit in control systems, and that's one of the reasons why like boiler temperature control is so significant. If you have, depending on the types of emitters that you have. So if I have really low mass heat emitters, it's less likely that I would end up doing this major overshooting. The higher the mass they are, the more that I have to recognize and understand the control of that. So just a little bit on that. So a couple of terms that maybe are somewhat different or newer to you. Operating differential and how that's different. So we're looking at operating differential right here and how that is different than the control differential. They are not exactly the same. So very good. All right, so what are some examples of on-off control? I just threw a couple of pictures up on here, and one example of an on-off control might be I'm going to turn the boiler on and off. I'm going to enable it. Maybe thermostat has a demand or some controller, and then we basically power up maybe this zone valve. So we energize the zone valve to provide heating. Another one might be, all right, we have a demand, let's go ahead and turn this pump on to provide us water flow. And then, of course, the last one that I have on here is in the lower right is a heat pump. So, for example, if my on-off two-position control says, oh, we have a demand for heating, so let's go ahead and energize this circuit. So these are all two-position on-off type outputs that are controlling these devices. So, and we have many systems out there that need that. Let's take a look at the next. The next one is what we call pulse with modulation control. It's called PWM control. Now, PWM control I see this as an advancement of somewhat I would call two-position control. So it's an advancement of this control of two-position or on-off control. And the advancement of the two-position control in this case here, what it's going to do is it is going to change the output, or let's say the length of the time, in this note that I'm putting here, it's changing the length of the heat based upon the amount of error or deviation from set point. So what will happen then is if the load is greater, then it's going to keep the cycle time longer, is what it's going to do. And if it recognizes that maybe I have a little bit less, maybe the error is a little bit less, then I'll reduce the amount of time that it has. So this is something where I've seen PWM controllers, output controllers control two-way valves, three-way valves and they will essentially determine how much time that they want to keep an output on to provide a signal. And this could actually be a variation of floating control even as well, and that's something that we'll be talking about next on here as well. So in the image to the right, I want to go through a couple little things just so we are good on this. So the one on the right here, we have what they call the blue line represents the target temp. All right, the blue line represents the target. The red line here, reddish orange, represents what we're going to call the measured temperature within the zone, or whatever it is that you happen to be controlling. It could be a zone, it could be just a water temp in a pipe, something like that. So that could be one thing. Then what will happen in addition to that is depending on where we are controlling to some extent, depending on that proportional band, what will happen is that at this point on the lower part on here, we're going to, if we ever reach this bottom one, we're going to turn that output on. Okay, this lower one here, it says output stays on if the temperature is below this line. So we're going to turn it on. Now it's in normal two-position control. What you would do is you would then say, well, I'm not going to shut off until I get all the way to the end, or to, let's say, the top of this. Now what this control will do, it has the ability to say, well, what if I turn you on for a little bit of time, and then I'm going to shut you off for a little bit of time. So in other words, this time span, okay, that time span from here to here, we've got this output on. And that's providing me some heating as an example. But then we're going to stay off, and then it's going to kind of relearn and figure this out, and it's going to say, okay, it took X amount of time to kind of learn this and figure out, well, how, it got colder X amount of time. Okay, so maybe the next time, because we're trying to figure this out, we're going to keep that output on, for a little bit of time. We're going to wait a little bit, and we're going to go from this point, and then we're going to shut it off, and we're going to let it coast. And what it's trying to do is it's trying to learn and eliminate the amount of error in there. So pulse width modulation control is a type that it does that. And the challenge in PWM control is recognizing when being able to diagnose this signal, whether it should be on or shouldn't be running. So a lot of that is sometimes you might have to provide a much greater error to see what is the signal doing. Is it turning it on or off? And then you might have to actually change the proportional band. If it's not advancing fast enough, you might have to manipulate the proportional band without, hopefully it doesn't hunt. And that's the one thing you have to deal with in there. There was a term that they talked about in your book that talked about when over time the average room temp that would become less than the desired temp, and that's true with electronic controllers. They will call that factor a droop factor, where it will just seem to always want to maintain a temperature that might be just slightly less on the average than what the actual temp is in there. So next thing, there is, and again, I just to re-highlight that, I guess in all, I would just say, with your PWM, the duration of the on, or let's say the duration of the on versus the off time is very dependent upon the error between the actual temp and the target temp. And that's primarily what we are doing. So the greater the error, the greater the on time to some extent on here, depending on where you are at. So in other words, in this example, being that our error is above, we don't need as much we don't need as much time. But over on the lower part, because if we're trying to control in this area, then we need more on time in order to make that to function. So that's pulse width modulation control. Floating control. So let's take a look at the floating control. So floating control, typically with floating control, usually we're talking about valves or actuators or control devices that are going to be what I would typically call drive open, drive closed type valves. They're generally going to be a valve where you have like you have really let's call it three positions. So in other words, you are either going to be, your controller is either driving a valve open, you're driving a valve closed, or the control output is off. Now this is not something you're going to use with it's not going to be used on spring return type actuators generally. If you are doing, let's say, static pressure control, and maybe you're using an actuator to send a signal out to a motor that's going to say, all right, I need you to speed up, or I need you to maybe control these set of dampers, drive them open, drive them closed. And you have a spot in the middle where it's not driving. What you don't want to do is you don't want to have it driving all the time. That would be basically hunting, and you want to try to find that sweet spot in there. In some of the controllers, I wanted to point this out here. So there's an image on the top right here, and I'm showing a mixing valve right there, and I have an open, a common, and a close type input to these controllers. So what happens then is I have to then define this or find this even on the controller that says, okay, which I will notice this as essentially a drive open, drive close type command. And what will happen then is the controller will provide me an output to say, okay, do you want to drive the valve closed, or do you want to drive the valve open? And they will never be this one right here. That is the contact to open the valve, and the contact to close the valve will never be closed at the same time. They should never ever be closed at the same time. It's either one or the other or neither of them, essentially is what it would end up being. And that's, again, you have to kind of figure that out. I've had some hydronic systems where I had a valve, depending on the way it's piped, you have to figure out, if I close the valve, does that give me more heat or less heat? If I open the valve, does it give me more heat or less heat? And so you may have to figure that out based on whether the valve is normally closed or normally open, and what its what its position would be. What is the mode that you're operating in? The picture on the lower part here is going to look at a system here where we're trying to control in this this floating area here, where we have kind of a range all the way from this big throttling range in there, what they're calling the control zone, and we hope that we can manipulate the on or off time to drive it open or drive it close a certain percentage to try to get it so that our control point and our set point equal each other. And that's kind of ultimately the goal. We want to try to reduce the amount of error on that to make this function. So it's a pretty neat little system. A lot of the commercial systems will use your 3-way and 4-way valves. So there's the first note on here says normally used to control 3- and 4-way valves. A lot of our mixing systems use floating control. Modulated DC output signal. So let's look at this one. And in our modulated signal, what we're going to do is this. We provide, out of the controller, we provide a variable DC signal to a control device. Now, I just put a couple of examples down here, and one of the examples is an output signal out of a controller. That would be, so we're talking about a modulating controller that's right here. I'm circling this in that yellow. And that modulating controller will provide me a voltage of maybe 2 to 10 volts DC. Or it could provide me an output of 4 to 20 milliamp as an example out of that device. And what it will do is it'll give me anywhere in between those values. So it'll give me 2 volts, 3 volts, 4 volts, whatever it might be, whatever it determines as the output needed, and it will manipulate or modulate that signal to some sort of a control device. So this control device has to match up to this signal. So the output signal and the input signal kind of has to be able to match up. Now, what we typically have to do, if you've got a system or a controller that let's say gives you an output of, let's say, 2 to 10 volts DC, that's an 8-volt span. And you have an actuator that maybe, just for simple math, I'll say operates between, let's say, 6 to 10 volts as an example, or 5 to 10 volts on there. What you'd have to do then is kind of scale it so that if this happens, if this were to be the case, you would want to have it set up that if the control signal is different than what the output of the controller will do, you're going to have to, what I wrote a note on here about scaling the output. So you want to say when the controller needs 0%, I'm going to give you whatever the low number is or the high number. Now you might say, why are you saying low or the high? It depends on the action of the output. So if it's direct acting, if it's reverse acting. So when you have 0% demand, what do you want the output? So a lot of this will determine on how you're going to control this particular three-way valve in this example. So it could be 2, it could be 5, but you have to identify the voltage that's going to be. So I'll just put a note on here, identify the voltage. Now, what will happen in some cases is I will go into the controller and I will actually manipulate or identify what voltage do you want at 0 volts. So then whenever my algorithm says I want 0% demand, this is the voltage I'm going to get. When I want 100% of the signal, then I have to also identify the voltage in this case. And by doing that, it allows the controller to kind of know what your device is. So I've had some controllers where they operated over a 5 to 10 volt signal, and I had a 2 to 10 volt type of a signal coming out of the controller. I've even had some that were 0 to 10 volt output with a 5 to 10 volt actuator. Now, rarely do we ever see controllers that give you 0 to 10 volts output, simply because of, let's call it, some of the noise that could induce a voltage on a wire that would allow, even though your controller thinks it's giving you 0 volts, it might actually be giving you 1 or 2 volts on some of these. So that's typically why a lot of controllers try to stay away. A lot of manufacturers try not to use controllers that give you 0 to 10 volts as an output, or ever having 0 as your appropriate input on there. So it's highly unusual to see that happen. The 4 to 20 milliamp, I want to hit up on that a little bit. 4 to 20 milliamp. So this one is a DC voltage signal. So for for testing a meter or testing a signal out of a controller into a control device, you really want to have an electrical meter that can just measure a small DC voltage, and it's really simple. However, when you have a 4 to 20 milliamp output signal, then out of a controller, and then you want to control a device that is a 4 to 20 milliamp signal, well, that's doable, but now for me to test that output, I've got to somehow get my meter in series. So in other words, the meter needs to be in series to allow you to measure what that signal is. So one of the things that I've had to do in the field to be able to do this is I had a controller that gave me a 4 to 20 milliamp output, and it went to my control device, and my control device, it operated over, let's say, a 2 to 10 volt DC signal as an example. Now, you might say, well, hold it, how can you do this? How can you have a 4 to 20 milliamp going into a 2 to 10 volt DC signal? Well, the way that we did this was at the controller. Now, it could be done at the control device as well. So this would be like a valve or an actuator of some sort. The way that we did this is we would take across the output, and we would take and put a 500 ohm resistor, and we would put it across that output. This is 500 ohms. And that 500 ohm signal will then take that 4 to 20 milliamp current signal, and it'll actually run some of the current through the 500 ohms, and it changes the signal to a voltage signal because of that resistor being in parallel. Now, I've even had some systems, and it's unusual to see that, but I've had some controllers that you could easily select, you know, do you want it to be voltage or do you want it to be current, and you would flip a switch. That's Honeywell makes a device like that. It's a really neat actuator that allows you to do that, and you can select whatever the signal that you want it to be. It's one of the neatest little systems out there. Belimo, there's other companies out there that probably are doing the same thing on there. So it's just one of those things where this has to get done in there. A good example I could probably relate to is when we look at economizer signals, and you know, sometimes this happens where you might have the control output operating between 4 to 20 milliamp, and your actuator is not even beginning to move once you're at 4 milliamps. It might not even be moving until you get up to 8 milliamps. So you really have to look at these things in your commercial applications as well. So it's a lot easier generally if everything matches up. So if your output and your control device are identical, usually you don't have to do a whole lot of scaling. But the more advanced you get, the more you have to look at it. So let's take a look at output controlling my heat sources. And the first one I want to deal with is simply on-off control with a single stage system. It's either all or nothing. And I got two images that are on to the right. The first one represents a typical building load. And there are certain times where we will have 0% or zero load, and there will be times where we'll have max load. Maybe the maximum amount of design load. Now, what I want to point out here, the bottom line represents a certain amount of time. Now, what I want you to see on item B is this is going to represent really the heat output using a single stage boiler. So I have a little picture of a boiler that's right above there. And what I want you to recognize is that, let's say that once I start establishing a little bit of load, the length of time that the boiler will need to run will be shorter. So that's a short on time. Okay. You'll notice the width of these lines start to become a little bit bigger. That means the on time is a little bit bigger. So when there's a very little bit of a load, what you'll recognize is that the on time, it'll heat up, it'll have a bunch of energy that it's putting in to warm up the boiler system and the mass of the piping and all this in your system, and with a little tiny bit of a lag, it's putting all this energy in there, but it doesn't really need all of it. It doesn't need 100% of that. So it basically heats it up and it shuts it off. Oftentimes with those things, you typically get a little bit of temperature swings in a system more likely than you would when it's a full capacity load. Then, of course, as the load is increasing into the building, it's getting a little bit colder outside, whatever it might be, you'll notice it'll warm it up, it'll figure out where the point it should shut off, and then it'll shut it right down in there. So that's, again, the length of time that it stays on will increase as you have more load on here. Now, in an ideal situation, I would love it if I had a boiler system. This boiler gave me the exact amount of BTUs that I need based on the building load. The reality of it is that just doesn't happen all of the time in most cases. So there's a lot of wasted energy in this type of control, but it's the simplest, and it's probably it's the most cost-effective in many systems or many applications. So we have to kind of look at that and use that as my example for what a typical single-stage heating system would indeed do. The next one I want to look at is controlling about multi-stage, so multiple boilers, multiple heating. And I could speak generically. This could be multiple chillers. It could be multiple heat pumps, whatever it happens to be. So there's a couple of things. What we would likely do is if I had two equally staged boilers. So for example, let's say I had a building that had a load of 200,000 BTUs as an example. 200,000 BTUs. Now, logically, we would divvy up those 200,000 BTUs divided by the 2, which would mean that I would need two boilers at 100,000 BTUs per boiler. All right, now, the nice thing about this is you'll notice that even though, yes, the load is small, here, the boiler we only will turn one of the boilers on in the initial stages, and we'll turn this one on, but you'll notice the length of time that one is allowed to run is going to be a little bit longer, and it's a little bit better match. Now, residentially, I would say you're not going to see too many people do more than 2 boilers, or 2 systems, or 2 heat pumps, just due to the cost. But commercially, we'll do even as much as 8. It would not be unusual in a commercial application to take what we used to have was a single boiler and maybe go up to as many as 4 to 8 boilers on a job, and there's some reasoning behind that. So in this example, again, we'll look at stage 1. At this point, this is an ideal situation where our boiler is providing 100% of the demand, and it's going to stay on all the time. Boiler 2 will then just kick on and off as needed, and just to try to satisfy and maintain that building load. And then when you're at the full building design load, which isn't that common, that normal, then that stage 2 and stage 1 are both going to be on in there. Now, the nice thing about this is the fact that you can actually have some backup a little bit. So if one of those boilers goes down, you can always switch it over to the other one. So that's actually a pretty good little setup on there. Very common to see that happen. The item C is going to look at on the lower, we're going to take a look, item D, on the lower picture, it represents the heat output out of 4 stages. So what you're doing is you're divvying this up between, the whole building load, and you're saying, all right, let's divide that equally up by this many stages. So a lot of our advanced controls can actually figure out when to stage these boilers, and they also can do some more advanced strategies, such as they can control and monitor the time that this boiler's been on and control other ones. So there's a lot of value that's in here. The fact that we can keep our boiler, like boiler 1 can just run steady almost, and then boiler 2, you'll notice that there's less cycling. And every time that I take a system and I cycle it, I lose energy every single time. And it's wear and tear on the controls. It's wear and tear on, let's say your boiler materials. There's stress with the metals for heating and cooling. So that's kind of the same type of setup. But again, most people commercially, this is more likely to be seen where they will do this. And from an efficiency standpoint, it makes a lot of sense. Let's take a look at the modulated output. So an ideal system, I'm going to look at figure 912 from your textbook. In an ideal system, I would love to be able to match perfectly the amount of heat that I can put out of my system, out of the heat source, as an example, if it's a boiler system. I would love to be able to match that heat output of the boiler to the building load in a perfect system where I would never ever have to shut anything off. I would never have to shut the heating system off. I could always maintain set points. That would be ideal. That's the perfect match on there. Now, the problem is that's really hard to find systems that will actually do this unless you have a lot of modulation and staging to do this, and we'll look at that. So in most cases, I would say a majority of our even residential jobs, they will only see turn downs that might be close to like 20% turn down. Now there are some that are out with as much as maybe can go down to 10% of the full capacity, but it's not super common. So if you have a boiler system that provides 100,000 BTUs as your output, or even look at the input, but the output on this thing, input or output, if you got 100,000 BTUs and you have a 10-to-1 turn down, you can actually provide as little as 10,000 BTUs. So that's, there again, I have to be able to match that out here. So let's take a look at some more on this. So in 913, and what we're going to do is this. So with our modulating control of this system, we are going to try to match the load to the capacity of that boiler by modulating, or by just giving you as little as it has to be. So in this example, or this picture, what we're doing is the boiler. In this case, we have a boiler with a 5-to-1 turn down in this example. So we can go as low as 20% of the capacity and 100% of the demand in here. So what will happen then is, as soon as we have the demand, the boiler will fire up at, let's say, at its 30% startup target, and then what it'll do is it'll recognize that, oh, we don't have the load, and it'll start to throttle back down to the low number, down to 20%. Now when it does that, you'll notice that it's then going to have to shut off. So once it shuts off, then we got to wait, and then all of a sudden it kicks in, it goes to the 30%, and it says, oh, we have too many BTUs, let's go ahead and ramp down to 20%. Now, it may, if it heats the space up appropriately, and it'll say, okay, then we're going to shut off. If the load is high enough, it'll just keep firing. So up into that 20-30% range area, and all the way up into this setup, everything up here, the boiler is on and it's not shutting off. That is really, to some extent, almost an ideal type of an application where we can really modulate these systems to try to make sure that we're not putting any more BTUs in than we have to. And we also have the ability to not shut the system off. And that's kind of the ideal way to do that. And then when the load gets really low, then we're sitting there at a cycling rate on here. And this is one of these where I think the thing that I would point out on here is, when you are doing any type of design in that thing, what I would say is this: watch your loads. Watch the size of the loads. The loads of what I'm going to say the zones. So if you've got a zone, let's say that's only 3,000 to 4,000 BTUs per hour, and that's one of your zones, and that's the only zone that's calling, and the boiler has to kick in, your boiler is producing 20K, but you only are using or needing 3 to 4K. So the problem I'm going to run into is it has to short cycle. It's going to have to run, heat it up, and then shut off. And that's just typical systems, normally have to do that. That's the less than ideal system, but we have to try to work through that. And of course, the ultimate and the final one that we'll look at here is looking at combining staging and modulation in a system. So my best application would be where I would maybe have multiple boilers, provides me the backup, provides me a number of things. We can match up the load, and we can have each of these boilers be operating and functioning. So what I have on the top left here, or in this lower left, is I have 4 100,000 BTU modulating boilers. Every one of these is 100,000 BTUs, and they all modulate. Now what I can do then is have anywhere from the lowest value all the way up to the highest value. So at max command, I can give you the full 400,000 BTUs of capacity of, each boiler being 100,000 BTUs. Now in the picture to the right, when I have less than what is really the needed at a 20% turn down, let's say, or at a, let's look at the turn down ratio, what we call the system turn down ratio. It's a little different than the boiler turn down ratio. A boiler turn down ratio would have been 20% of the 100, or in this particular case, it would be a 5-to-1. But in this case, we have 400,000 BTUs, and one boiler kicking on provides you 20,000. So in this case, my system turn down ratio ends up being 400,000 divided by the 20,000, which is providing me as, in this case, a 20-to-1 system turn down ratio. So under those low loads on a large system, I can really do a nice job of controlling the output and trying to control temperature without having to cycle the boiler on or off. It can stay running as a pretty good. So that's really the ideal setup on here. But so in commercial control systems, residential control systems, we still need to have a good understanding of the control fundamentals of different control algorithms, how we control certain outputs, and what I have to kind of know to be able to do these types of things.